Yeah. Hi. Good evening. Welcome to the week two problem solving session. Okay. Of selected algorithms, selected topics and algorithms. Again, my name is Bhavya, and I'm a PhD scholar from IIT Madras. Again, to remind the others who may be watching the recording, we'll be having uh, these problem solving sessions every 6 p.m. 6 p.m. to 8 p.m. Okay. Okay. Good. So let me begin directly. So what were we talking about last time was flows. Okay, and I've already done a recap last time about what flows are and so on, and what were the algorithms. We discussed two algorithms, that is Ford-Fulkerson algorithm, and next one was Edmonds curve. Okay, these two were discussed last time, and this week's topics are as follows. Okay. Uh, a slight idea on flows, uh, which is the first is what is called a fattest augmenting path. But I'm not going to cover anything here because the ideas are pretty straightforward. It's almost like Edmonds curve, but with using weighted paths. So I'm not going to cover this. And the other is what is called the max flow min cut theorem. I'll get into this later. And then what do you have? We have matching using flows, and matching is a large area out of which we are just uh, sampling a drop, and another one is maximum matching. Okay, actually both of them are maximum max flow min cut matching um, algorithms, which are of two kinds. One will look at bipartite case and non-bipartite case. Also, I was going through the assignments. I noticed that the assignments are in a slightly incorrect order. That is, the week two content is asked in the week one assignment, and week three content is asked in the week two assignment, and so on. So yeah, that is an unfortunate thing. I contacted the instructor of the course, and then he said week four onwards it will be fine. I think week one deadline got slightly extended, therefore. So I think week one assignment deadline is tomorrow, right? So that issue is partially settled right now, because week four onwards it won't be a problem. So no need to worry about that. Okay. And okay, Sandhya is here. Kishore is also here. Okay. So this is this week's topics. And before we move on to this week's topics, I want to finish this question, okay, which uh, I had written last time. Okay, this week too, okay, and I had left last time's tutorial hanging on this question, saying that this is, say, a homework problem. So maybe you guys thought about it. So if you guys thought about any solution, please let me know. Um, Hello, am I audible?
Yes, you're
Yeah.
audible.
Okay. I'll in case you do not recall, I'll explain the question once again. There's a food truck company here, which is what they're called Srinivasan Food Truck Company, and it can only produce a limited quantity of food items per day. It wants to implement a sophisticated lunch ordering system where customers pre-order their food and underlying algorithm optimizes the food allocation in the following way. There are n customers, m types of food, each with quantity Q1 to Qm. There are m types of food, and each of the food item has quantity Q1 to Qm. Okay. Each customer CI pre-orders a set of one or more food items, and their set of food items is AI. Okay. So the algorithm allocates to each customer CI either one of their choice from the set AI or a 20 rupees voucher as compensation. Okay. So let me write it down. Oh, why are there so okay? Select and delete. Okay. So yeah. So what the question is saying is that there are n customers, okay, and they are C1, C2, C3, and so on till Cn. Okay, and there are m food items. Okay, and there's food item A1, food item A2, food item 3, A3, and so on till AM. Okay, so you can imagine them being some burger, pizzas, idli, dosa, and so on. And now each of the customers, they want to pre-order their food, okay, to that food truck company. But the problem with the company is that it can produce only so many items per day. Okay, and so there is a quantity constraint. So food item of A1, there's only Q1 amount, Q1 units, okay, and Q2 units of food item A2, and Q3 units of food item A3, and so on till Qm. Okay, now let's say customer C1, okay, and customer C1 puts in the app that okay, I would want either this, either that, or that. Okay, for example, customer C1 would say, C1 says he wants one of, so this set will term as A1. Okay, one of, say, food item A1, any one, okay, any one of food item A1 or A7 and A8. And similarly, C2 says he wants any one of the set A2, which is say A1, A8, A9. And C say 7 says he wants any one food item out of A8, A7, and that's it. Okay, and this is sort of what is happening. And what you want to do is as follows. What they will ask is design. Okay, so the algorithm allocates each consumer CI either one of their choice from the set AI or a 20 rupees voucher as compensation. Okay, so for example, let's say A1, customer C1 is allocated food item A7, okay, and C2 is allocated food item A8. Okay, so customer C1 is allocated A7, customer C2 is allocated A8. Okay, now what is A7 allocated with? Well, A7 wants either A8, food item A8, or food item 7. But let's say quantity of food item A7 is exactly 1 and quantity of food item A8 is exactly 1. So there are only two food I mean, there is only one unit per food item here. Okay, and A7 requires food item A8 or food item, but it's over. It's over now. You already gave it to customers A7 and A8. Okay, these are the quantities. So it's already over. So what will happen to A7? A7 is given a 20 rupees voucher. Okay, and this is bad for the company. I mean, there may be cases where you cannot escape this, but for example, what would be another way to do this instead of allocating it this way? Can you do it without giving a 20 rupee voucher? Is it possible in this scenario? Of course. Yeah.
We can reduce the vouchers, but we cannot say that 100% we can. I mean, the company won't get incurred of 20 rupee vouchers 100%, but we can, to some extent, we can reduce by the improvisation of algorithm.
Probably we can reduce, right? And I mean, yeah, like you said, Kishore, we cannot guarantee, maybe, but
So
I'll come to it. Yeah, yeah, go ahead.
so yes, so we can do one thing that I can give A1
Mhm.
plus A1 to small A1 to the customer C1.
Okay,
This is
C1 is given A1,
yeah, and then customer C2 is given A8,
A8.
and then C7 can be given say A7.
Ah, okay, right. C7 can be given A7. And this is one way to put, yeah. So this is one way to minimize um, the number of vouchers given. So in this case, we've reduced the number of vouchers to be given to the customers by one. Right? So maybe we need to give vouchers to others also, some A6, A8, and so on. But at least to these three people looking at this, you can actually do away by giving fewer vouchers by using this slightly smarter way of allocating, distributing them. Good. So yeah, now I want to come to the point that Kishore was saying that um, we cannot guarantee that we will always require. We cannot guarantee that there is a. We will require 20 rupee vouchers. We cannot guarantee that, and that is true. For example, let's say. For example, let's say A8, A9, and for example, if okay, so let's say customer this C7 exactly wants food A8, and if two people want the same thing basically, and let's say customer one also wants A8, then you cannot do anything about it. You need to give someone a 20 rupees voucher. You cannot do anything about it. Okay, and the answer is no, you cannot guarantee that you will not require any 20 rupees voucher. This is clearly a counter example that you will definitely need to give a 20 rupee voucher either to customer A1 or to customer A7. Okay. Now, but the question is not asking that. Okay. The question is asking something else. Question is asking find a strategy so that you can find the minimum number of vouchers given to be given. Okay. And surprisingly, that is possible. It is possible to guarantee that you can guarantee that this particular assignment is the minimum way to give 20 rupee vouchers to everyone. Okay, so that is possible. So that is what the question exactly asks. So design an algorithm to minimize the number of vouchers given to customers. Okay, so design an algorithm to minimize the number of vouchers given to customers. So last time I gave you guys a hint also, saying that minimizing number of vouchers is same as maximizing food allocation. I think everyone agrees with this. The the more people I allocate food, yeah, sure.
Yeah. Just before you say,
Yeah,
I was just trying to analyze it within this last a week.
yeah, yeah.
Uh, so just wanted to put forth.
Sure, sure,
Maybe it's a wrong or it's a right. I'm not sure,
sure,
but
sure. Just let
see,
me know what it is. What is it?
yeah. See, as we said, C1 to CN, and then Q1 to QN, and then the other one is
Yeah,
the quantities. See,
right, right.
let us suppose what we can do is on the quantities, right? On the ordering, we can put an mutually exclusive lock, and then when someone is ordering, right? Of course, for the first orders, probably all the quantities will be available at 100%. The threshold will be 100%. So the first order peoples who order at first will be getting all the orders, but the only case we need to uh, look at is as the time passes, the quantities reduce, and then even items also closes at few orders. So that time, right, probably what we can do, once someone orders, right? See, let us suppose we have a what do you say, items, 10 items, 10 food items. So let us suppose item number 10 has been already completed, and then order, that was the order by 11th order by someone from the group of customers. So the 11th order, it checks whether the what do you say, the order is available made by him or not, and give the available suggestions. So this order is completed, and these are the available food items, and then these are the number of quantities available. We can give suggestions to that customer, so that at that point in time, what are the orders are available. So
Yeah, yeah, okay. But
even then yeah.
yeah, okay. But okay. Uh, so here you are saying that okay. So the question was not framed with the timestamps in mind, like when they will place the order and so on. I can see
Yeah,
that what you are saying is that um, if someone is ordering earlier than the other person the same food item, then the person who ordered earlier, it should go to him.
right.
Right. In fact, what you are saying that if the food has already ran out uh, before it someone orders it, then it will be displayed to that person that okay, the food has already run out, it's out of stock.
Right. So
Right.
see, yeah,
Right. Right.
if the quantity is available, and the order is matching to the quantity available, then the order swiftly will be confirmed to that customer.
Okay.
But
Okay.
the matching is not available. I mean, like, if it doesn't match, then the suggestion should be made, or else at the least, you should give multiple suggestions to the customer, and then at last the customer doesn't pick any one of the available suggestions. Probably that time the 20 rupees voucher should be given.
Ah, yeah, but that is a very real world scenario thing where you might give some alternate suggestion. But this problem, let's say you are not allowed to give the same, you are not allowed to give alternate suggestion. The customer only wants his set of food. Either he wants one from his set or he wants a 20 rupees voucher.
Okay. So in that case, right, probably first, when the order comes in, right, we should check the in the set what he has been suggest. I mean, what he has been wanting for, and then if the quantity is not available, probably we can go for the other set of food items which is available, and then should be confirmed to that customer. Even then, the customer doesn't accept. In that case, only the 20 rupees voucher can be given.
Okay, but how do you prove that this is an optimal strategy? That is first thing. And secondly, let's say two customers are ordering at the same time, at the same timestamp.
Yeah, that's what I was telling. We should put in a mutually exclusive lock. Probably in algorithm terms, what it should be, I'm not sure, but based on the technical things, right, it can be possible. See, if
Yeah,
someone is
let's say
ordering,
you're
just like a
implementing a
banking,
locking mechanism.
yeah, just like a banking transactions, we do it, right?
Sure,
So
sure.
That's how we can make implement that strategy over there.
If you're doing a locking system, okay, then maybe it is possible. But the locking system also has its it's based on the fact that you have a single processor machine, and that lock,
Okay.
you need to fight for that lock, and then once you get the lock, and and the advantage there is that the number of threads that are there in that process is only finite, and therefore you can obtain only finite number of locks. But let's say the computer that is doing is not, since we are talking it from a very algorithmic perspective, we don't see how powerful the computer is, and you see what I'm trying to say. So it does not depend on those kind of factors. So that's why I'm asking you, let's say not just two people order at the same time. Okay, I know this is a very strange scenario, but let's say all of the customers C1 to Cn, they order at the same time, to the minute, to the dot. Okay, or
So what you say is he'll pick all the orders at once. I mean, then complete taking all the orders, then he will deliver. That's how you are saying.
yeah. First take all their orders, because that is what the question does not say when they order and so on. They just say the customer C1 M types of food items. Each customer pre-orders, algorithm allocates to each customer and so on. But there is no question about timestamps. They are not saying how the preference, first come first serve, nothing like that.
Okay. See,
So
yeah, I can see pre-order. It says pre-order.
yeah. So it says pre-order, and let's say there is no idea of first come first serve. Okay, because it may so happen, because see, I'll tell you why. Okay, it may so happen that I'm the first person to order. Okay, let's say, okay, I'll give you an example. I'm the first person to order. Okay, C1, I'm the first person to order. I can have A1 item, food item, A2, A3. Okay, these are my choices. Great. Now C2 can have A A1, A7, A2. Okay, and C3 wants to have A1, and that's it. Okay, so let's say the quantity Q1 is 2, quantity of um, A7 is 1, quantity of Q2 is 1, quantity of Q3 is 1. Just arbitrary, okay, things. Now, like you said, in the timestamp ordering, I'll do the first come first serve business. Okay, so customer 1 walks in, he says, I want either anything of A1, A2, A3. Oh, I'll say, oh, I have 2 Q1s and 3 Qs. So I'll have one each of Q7, Q2, Q3. So I'll give them 1 unit of Q1 and be done with it. So I have left 1 unit, and then A1 is allocated 1. Customer C1 is allocated food A1, and then C2 has this A1, A7, A2. Then C2 says, C2 looks at his order, and then the algorithm looks and says, okay, I can pick any one of these, and then I'll again give them Q1. So I've done, and then I realized that, oh, okay, C3, customer C3, I cannot allocate him his food only because he wants exactly A1 as his food item. So when you add this time constraint, okay, it actually becomes a harder problem to solve, because you cannot predict what the next guy is going to order. So C3 needs to be given a 20 rupee voucher. Whereas if this time thing was not there, everyone had placed their order already, then what can I always do? I can give A3 to customer C1, I can give A7 to customer C2, and then I can give A1 to customer C3 and be done with it. Now that all the information is already available, right? All the information is already available. I can do my running of the algorithm is easier.
Okay.
right? You can see that. So um I don't want to dive too much into it, but the kind of this kind of algorithm is what is called an online algorithm. Okay, you may have heard of it. Online algorithm is it is used by banking systems and maybe these big food delivery people and data analysis companies. There's a constant stream of data. You cannot predict easily what the next item is. So this is an example of an online algorithm. Another scenario is when you know the timestamps already. Okay, you are doing it in batches. Say C1 is doing at 5 p.m., C2 is doing at 6 p.m., and C3 is doing at 6:30 p.m. These timestamps are already known to you. Maybe that is also way you are thinking about it. Sure, the timestamps is already given to you.
Yeah.
Yeah, right. This could also be a situation, and then you can also talk about precedence and so on. That is also an example of a matching algorithm. Okay, but this kind of questions are a generalization of a specialization of what are called the hospital residence problem. So it's like you have a hospital where there are so many patients and only so many beds. Then how do you allocate to them? Now, like you said, there's timestamps, right? And you can even say things like, okay, some customers have a higher emergency than the others. Now there are weights associated with each of the edges and so on. So how do you, which is same as your problem, right? There are weights. These are somewhat like weights. A high C1 has a higher weight. I mean, it is contradictory because he has ordered or earlier, but earlier means more urgent for us, which means higher weight for us. And so you want to maximize the amount of weights in the matching and so on. This is the variation of hospital residence problem. But what we are looking at is not a hospital residence, not a weighted hospital residence problem. We are looking at the unweighted hospital residence problem, which means we don't have a ordering, we don't have a precedence. Okay, everyone assume that everyone is ordering at the same time, either that or assume that everyone has already ordered. We don't care about who has ordered earlier and after. Okay.
Yeah.
Okay. Okay. So, but good. So, yeah. Minimizing the number of vouchers is same as maximizing food allocation, because if I if I feed more people, it means I need to give less vouchers, and vice versa. If I had given more vouchers, it means more vouchers than optimal. Then it means I can still maximize food allocation. Okay. So, let's see. Another hint is that use flows. Somehow use flows to actually achieve this. Okay. Question is, how do you use flow to achieve this? So, any idea what should be the vertices? What should be the edges? Let me remind you what a flow is. Flow you can imagine as water flowing through water pipes, and where each of the edges has a capacity which is akin to water pipes having their upper limit on how much water they can supply through themselves. Okay, and Kishore.
See, we can take customer as a source and then food or food as a source vertices and then customers as sink edges. Sorry, not sink vertices. And then for the edges, weights of the edges, we can take it as the quantities of the.
Okay, good. Yeah, good. Okay, so either take customers as source or sink, and vice versa for food items, right?
Right.
So we can try both. So first I'll have customers as source. C1, C2, C3, and so on till Cn. And here I can have A1. Oh, yeah, go ahead.
So I have a point here that customers should be made sync only and cannot be source.
Okay, sure. Okay, so Goel's, your idea is customers should be made sync. So this is your idea, C1, C2. And why do you think it should be sync?
Because I think that then otherwise, how would we verify that whether to give a 20 rupees voucher or not, or whether the requirement is getting fulfilled or not? So if the customer C1 is getting the items of his choice,
Huh.
so that we can verify that whether to give the voucher or not.
Okay, okay. To verify whether we've given the voucher or not. Okay, okay. So let's try to think through the strategy. Okay. Now, what I want to do is maximize the amount of maximize the number of people who are fed, which means I want to somehow relate it to maximizing the flow. Right. So here is an idea. Yeah, that is first thing, the quantity. Okay. Another important fact is each customer should be allocated only one food item. So somewhere that idea of at most ordering one food item should exist. So at most ordering one food item can go in as a capacity constraint. Okay. Q1 to QM can also go in as a capacity constraint. Q1 to QM can also go as a capacity constraint. But it is talking about how much food I can at most order. So here is the solution that I have in mind. Okay. So the solution that I have in mind uses the first approach, that is customers as source and food items as sink. Okay. Customers themselves can order at most one food item. Okay. So he can flow. Okay. So let's say C1 can order A1, A2, A3. Right. So I'll do A1, A2, A3. Okay. A1, A2, A3. And he can order only one of these, remember. So I'll add a flow capacity of 1. But let's say I allowed customer to get a source input of 3, let's say. Okay, then he can order even A1, he can simultaneously order A2 and simultaneously A3, because these edges are also carrying, can be distributed. Flow conservation is still maintained. I can make this flow, make one flow through each of the edges, one unit of flow through each of the edges. We don't want that. So what is the solution? I set the source to customer 1 as 1. Okay. What does this mean? If customer 1 is sort of having like 1 rupee ticket, okay, and he can only buy one of these items, because customer 1 can either make his flow through the first edge or the second edge or the third edge. He cannot make it flow through 2 edges or 3 edges at the same time. Okay. And similarly, C2, he also has 1 unit given to him. And then what will C2 do? C2 is ordering A1, A7, A2. A1, A2, and somewhere A7. Okay. Let me make balls. A7, A1, A2, A3. Okay. And similarly, C3 is ordering only A1. Okay, this also I'll change. C1, C2, and C3 is ordering only A1. Okay. Now I hope you can get the idea of what is happening. Right. At least this case is handled about any customer only being able to order one item. at most, not multiple. So, and so on. Now, can you think? I'll give you a moment. Can you think of how to implement the quantity constraint, the quantity that they cannot? I shouldn't be able to order too much of A1. I shouldn't be able to order too much of A2 and so on. Yeah.
So like say, uh,
Yeah.
so I think that so quantity now that we would be introducing a separate sink also.
Okay.
So since we would be using a sink, so whatever sum we are getting here, I mean that sum. So whichever arrows which are pointing towards A1, their sum should be less than the value Q1.
Good. Yeah.
This is
Okay.
constraint.
Good.
So if that is the constraint, then okay. So fine. So
Good. You are very close. I mean, you just need one more step and that's it. Yeah. One additional thought and
No,
that's yeah.
exactly. The total output should be only one. So of course, because
Total output should be
we
only
have
one, meaning?
right, because only one quantity it has to be delivered, right?
Yeah, yeah. No, but that is taken care of. That is taken care of because the flows now C1 cannot order multiple because C1 is only getting 1 unit of flow. He can only send 1 unit of flow here. He cannot send simultaneously to A2 and A3. He needs to send it, choose between them. But how do you implement the quantity constraint? They shouldn't be able to order the allocation should not be more than so it cannot be that say C1 is allocated A1, C2 is allocated A2, C3 is allocated A3. Okay, because all of them want A1, right? Let's say C1 is allocated C1, A1, C2 is allocated A1, C3 is also allocated A1. But let's say there are only 2 units of A1.
So then I can draw an edge from A1 to the sink, and then on this level, I assign the capacity, but capacity in the reverse order kind of the thing, negative value probably.
Negative.
Not negative because something. I mean, things should be preserved. So if I getting three values coming towards A1,
Huh?
then I mean whatever is going out of the A1,
Huh?
that thing should be smaller than the capacity. So yes, that is absolutely fine. I mean, we can draw an edge having the capacity say Q1, and then from A2 to T having the capacity Q2, and then so on.
Right, right, right. Q2, Q3, and QM. That's right. So look at this construction. Good. So look at this construction and see that everything is satisfied. The fact that S can send 1 unit to each of the customers means that since flow in is equal to flow out due to flow conservation, C1 can either choose A1 or A2 or 3. Okay, A3. And okay, sorry. What do I mean by it's satisfied? I mean that max flow of this channel is exactly equal to the maximum units that you can allocate. Yeah, Kishore, can you? Yeah.
Yeah, but we are not maintaining the flow conservation, right? See, from S1 it is 1 to
Huh.
C1, but from C1 it is 3. The flow conservation is it's not satisfied because
Where is the flow conservation not? Oh, these are capacities, by the way. These are not the flow. These are the maximum capacities of the channel.
okay, okay.
Okay. So, yeah, sorry. What I meant by flow conservation is satisfied. I mean, the other way around. Sorry, yeah, I should have been more specific. I meant if the because of the flow conservation property, C1 cannot send. That is what I meant. Sorry, yeah, C1 cannot send more than one unit of flow, and so it therefore it cannot send flow through multiple channels. Okay.
Yeah.
Okay. So the trick is now we look at the maximum flow here. Okay. The maximum flow of the channel would correspond to the maximum food allocation.
So if I do not have one value corresponding to the edges in between C1 and then A1, say C1 and any of the A1, then that will result into a 20 rupees.
Yeah, can you say it again once?
Yes. So if the value is not one, for any age that is emanating from C1 and coming towards the A's, if none of the age is carrying the value 1, so then this will result into a 20 rupees voucher.
Yeah, exactly. So let's say you run the max flow algorithm. Okay, you run the max flow algorithm, and it so happens that there is a C somewhere, okay, through which no flow is going. Through none of his channels flow is going. So it means he has no food allocated to. Okay. Just one moment. Sorry. Okay. So I mean, it's possible to prove this also if you're not convinced. Again, there are two parts to this problem. One is the number of food items that is allowed per customer is 1, and the number of food items that is allowed at the number of food items that are allocated to customers should not exceed the total quantity. So through the flow, it may be that C1 is ordering A1 and C3 is also allocated A1. Okay, this constraint, capacity constraint, is stopping C2 from, let's say, ordering A1, because let's say Q1 is the value is 3, so you cannot order. Q1 value is 2, so you cannot let C2 order. So C2 needs to flow through this channel. So this is exactly capturing this problem, right? Okay, Kishore, is this fine?
Bit skeptical to me.
Yeah.
I'm a bit skeptical on this.
Sure.
Based on the first two properties, right? We should maintain the flow constraint and then flow conservation. Those things, that's fine. So because the flow constraint is something, the input, how much input we get, the output no, flow constraint is the total number of quantity should be less than the flow, how much the flow, exact flow is flowing. The flow conservation is how much input we get, the same output should be as an outflow.
Yeah.
Okay. So here, see, let us suppose from S we are getting 1 and then into C1. Okay. But C1 has multiple routes or multiple edges, which is making around 3 units. Of course, it is getting only 1 unit as an input, but it is outflowing it has a capacity of 3 units.
Outgoing capacity is 3. Yeah, sure.
Yeah. So that's where the flow conservation property is it's breaking, right?
No, it's not breaking. It's helping. The fact that flow conservation says if I'm taking 1 unit of flow inside, then I should spit out exactly 1 unit, not more, not less. So let's see. These are just capacities. Right now, no flow is assigned. it can even be that, okay, I'm not giving any flow to C1.
Okay.
So it can even be that I'm giving no flow to C1. But if I am giving flow to C1, then C1 should choose one of the edges. Okay, out of the capacity, it needs to flow 1. So sorry, yeah. So right now, before these labels are just capacities. Okay, these are just capacities. Nothing is flowing through this. This is just a construction of the weighted graph. I'm not saying this is the answer. I'm saying once you run a max flow algorithm through this, that will give you the answer.
Okay.
Okay. Now, Kishore, what I'm saying is, once I run the max flow algorithm, I'll find a way to give the maximum of flow from S to T in the network. Okay, the maximum amount of flow. So, what is the maximum amount of flow that reaches from S to T is same as the sum of the flow through S going outside of S, which is same as the number of C1s which are giving non-zero flow outside by the flow conservation principle. Okay, once I start allocating the flow, of course, right?
Yeah.
And once you say that is the maximum, so which is nothing but the maximum customers who are getting food, right? And this food is not exceeding the quantity that they are ordering. It is not exceeding the total quantity of the items because of this constraint, capacity constraint, because the capacity is Q1. Okay, so let's say C1 is ordering A1 and C3 is ordering A1, and Q1 was equal to 2. Okay, then I cannot make this flow. I cannot make C2 push flow inside A1 because the capacity of the outage of A1 is 2. So it can, so if I push 1 unit of flow here, it means in unit is 3 and out unit is also 3, which is not possible because of the capacity constraint, because Q1 is equal to 2.
Right.
So is that clear?
Yeah.
So this is a way to actually use flows. Another way, I mean, we already saw one application last time, and this is another application of flows. Okay. Okay. Good. Okay. Okay. So that was the first question. Now let's look at the second question. Okay. Oh, okay. Okay. Let's quickly move on to the next question. So next topic which I want to cover, which is called the max flow min cut theorem. Okay. Max flow min cut theorem. What does it say? It says, okay. First, okay. I'll just say, okay. In a weighted graph, G, V, E, and the weights W. Okay. In a weighted directed graph. Max flow through the network. Okay. S to T max flow is equal to the size of the S to T min cut. I'll tell you what S to T min cut is. I'll recall it. But first, what is a cut? Okay. A cut is a set of edges that disconnects the graph into two components. Okay, and that is cut is a set C such that when I remove the set C from G, okay, which is denoted by this backslash sign, okay, I remove those edges, okay, induces um, two vertex partitions X and Y such that the edge set of X and the edge set of Y do not have any common edges. Nothing is going through. What is, for example, okay, this is a graph A, B, C, D, E, F. Here, AC is a cut. Oh no, AC is not a cut. Not AC. I need a AC. AC along with AB is a cut. Similarly, B, F, FC, and FE is a cut. Okay. Why? AC and AB. AC and AB is a cut. Why? Because if I remove the edges AC and AB, AB I remove, AC I remove, then I have two connected components. One is A and the other is this, whatever this is. Okay. Similarly, BF, FC, FE. BF, oops, FC, FE. Two connected components. I can have a bigger cut also. For example, if I remove, okay, let's say I remove AC, BC, FC, BE, and FE. If I remove this, then there will be two connected components. One is ABF and the other is CDE. But what is a min cut? A min cut is a cut of the smallest size. And you can see that this is the smallest size possible. I cannot have a smaller. What would mean that I have a smaller cut? It means that I can remove just a single edge and disconnect the graph. If you look at this graph carefully, then you need to remove at least two edges. That is, I need to remove this to disconnect the graph, or I need to remove this to disconnect the graph. Okay. So that is the definition of a cut. So min cut is size of the smallest cut in the graph. Okay, that is min cut. And okay, so can you tell me a few things? Can you tell me for a cycle what should be the minimum cut size? Given a cycle. Let's say this is a cycle. This is what is called a C6. Six-length cycle. Oops. What is the minimum cut size?
1 edge. 1 edge is more enough for this.
1 edge.
2 edges.
2 edge. 2 edges.
2 edge, right? So you will see that even if I remove 1 edge, it is still connected always. So I need to remove any other edge to actually disconnect the graph. So for a cycle, the minimum cut size is 2.
So
Yeah.
so if the degree of a vertex is 2, right?
Degree of a vertex is 2.
So can the vertices and
Yeah, sorry. Can you say it again?
so can we examine the degrees of all the vertices of the given graph?
Can we?
And can we examine the degrees of the vertices of the given graph?
Can we examine the degree of vertices of every graph and?
Yes, and focus on the vertex having the least degree, and probably that would be the value of the min cut, because those many edges.
That is that is a lower amount on the minimum cut. It is not the exact value of the size of the.
But at least we give some idea. I mean the lower bound, yes.
Yeah. Right. So what Goel is saying is that look at a graph and look at the degrees. Okay, degree is the number of edges incident on that vertex. Okay, and let's look at this is a graph. Look at the degrees. Goel is saying that, for example, degree is 4 here, degree is 2 here, degree is 3 here, and degree is 1 here. He's saying that the minimum, the size of the minimum cut is the minimum degree of the graph. Okay, and so why? Because, for example, here the minimum degree is 1. I can just remove this edge which is incident on it, and therefore I can say it is the minimum degree. For example, if let's say this was not there, let's say this edge was not here, then the minimum degree in this graph is 2. So I can remove these 2 and then be done with it. So that is the argument, but that may not always be true. Okay, it is true that this is a lower bound, which means minimum cut is at least the minimum degree of the graph G. It is at least the minimum degree of the graph G. I mean, okay, sorry. It should be at most the minimum degree. Sorry, it's not a lower bound, it's an upper bound. It is at most the minimum degree, because it is true that I can always disconnect, choose these edges and disconnect the graph. So if I say find a minimum cut, it will always be smaller than this, because this is always a trivial example. Yeah, good. Okay, that fine, right? Well,
yes. And what are we trying to achieve actually? I mean, what do we find about? What do we need to find through the min cut? What else we want? I mean, except so why this value of the minimum degree is not the final answer?
And why is minimum degree not the final answer? Because minimum degree is an upper bound. You can actually do better in some cases. That's why.
Yeah, fine.
Okay, that's why you can. There are cases where you can do better. For example, let's say. Okay, what are the degrees here? 2, 2, 2, 2, 2, 2, 3, 3. But what is the cut size, minimum cut size?
Yes. 1.
1. This is a counter example, right? The minimum cut size is 1, but the minimum degree is 2.
But then we can always, make this statement that in the absence of a bridge, the minimum degree is the answer, and in the presence of the bridge, The 1 is the answer.
Yeah, I mean, I'm not sure whether that statement is true, but there is a certain, I think it's called bridges only. A graph theorist will be able to answer that question. It may or may not be true. I'm not sure about that statement. That this is the
So
only
can
kind
you
of counter example that you
can
can give.
so can you give a counter example and without a bridge?
Yeah. Right now,
Because
I cannot think of a counter example, but it may be true. It looks like it may be true. To
yes,
achieve it without such kind of bridges, having okay, it should be true. It should be true. But a
yes,
bridge is exactly what is a minimum cut, right? So it's sort of the same thing now. Now that I see it, cut is nothing but you can always draw a graph in this form, and this is a cut,
yes, yes.
right? So yeah, it would be true. But there are several interesting characterizations of cuts that it's studied in graph theory, but it's been a long time since I've seen those kind of characterizations. Yeah, Kishore.
See, of course, we are doing min cuts, and then based on the statement min cut max flow. But exactly what we are trying to prove here, and then where is the exact application of this min cut when we come to a real time application, and what we are going to achieve for this.
Yeah, sure. So, min cut max flow, for example, um, you will see that you already saw how useful flows were, right? In allocation problems and so on.
Right, right.
Min cut is also has several applications. For example, min cut. Okay, I'll give you a direct example of a min cut. Okay, a direct example of a min cut is um, to find network bottlenecks. Okay, what I mean by that is min cut is sort of the thinnest part of your network. What do I mean by that? Let's say this is a graph. Okay, this is a graph. And now this is network lines of a country, let's say. And there is an enemy country. Okay, it wants to disrupt the internet connection in my country, let's say. So what can it do? It can start destroying my network. Okay, it can come to this place and remove this guy. It can come to this place and remove this guy, and then it can remove say this guy, and then I'm still connected. I still have internet working in my country because there are other channels through which this vertex can communicate, and then it will destroy this guy, and then it will destroy this guy, and finally he has disconnected this part of my country's communication network. But he could have done a better thing, right? He could have disconnected this place, for example. And just by removing 3 edges, he is doing already better. So this is actually showing a vulnerability. Imagine now you have billions of nodes in the network. How do you identify which one the country will choose to attack? Or if I am the attacker, which one do I choose to from the billions of nodes, right? So what are cuts? It is nothing but a set of edges, like Goel was saying, it's like a bridge. Okay, I can always draw my graph into 2 parts such that the cut edges are going across those 2 parts, and the min cut is the graph where this is the most thin. Okay, this is a min cut. This is a cut actually is divided into parts x and y, but if it is thinnest, then that is called the min cut. Thinnest possible way of drawing it into this way. So it is the thinnest set of wires in my internet, inter LAN network, whatever. Okay. On removing that, you disconnect the entire graph.
Yeah.
Okay. And that is one, say, application of mincut. Okay. That's a very practical application of mincut. There are also abstract applications all over the place. And another application is that you can actually design flow algorithms using mincuts. Match flow algorithms using mincuts. But here the mincut I'm talking about is actually a different mincut. Oh, okay, good. The mincut is slightly different in the sense that this mincut is about a weighted mincut. Okay, this is about a weighted mincut. Okay. So now what is a weighted mincut? Weighted mincut. Okay. Set of edges that not only form a cut. Okay, I'll call the set of edges C, again subset of edges that form a cut. Okay, and that is the disconnect the graph, and for all set of edges C prime. Okay, the number of edges in C is the minimum. Oh, not the number of edges, sorry. The weights of the capacity. The sum of the capacities. Sum of the capacities of the edges in C is the minimum across all C. All C prime. Okay, or I can remove. And minimum across all C prime subset of E, same thing, summation capacity C E in C prime. So this quantity is what is called the capacity of a cut. It is nothing but the minimum capacity across all cuts. Okay, sorry, minimum capacity across all the edges in the cut. What do I mean by that? Well, what I mean by that is, if I have a network like this, if I have a graph like this, and let's say capacity is 10, 1, 20, 3, 45, 7, 8, 9, 10. Okay. A cut is any edge that disconnects the graph, right? So what is an example of a cut here? This is an example of a cut. It disconnects the graph. Okay. That is one example of a cut. Another example of a cut is this. This also disconnects the graph. According to our previous definition, what is the min cut? According to previous definition, yeah?
Minimum number of the edges.
Minimum number of edges, yeah.
Yeah.
So in this case, it's the this edge, right, where 45 is written. It's just a single edge. Removing that disconnects the entire graph. Right.
Yes, but then this is not the answer here, because we have to minimize the sum of the weights as well.
Exactly. We are looking at weighted min cut. We are looking at weighted min cut. So we are looking at weighted min cut, which means that it's not just I need to disconnect the graph. I need to make sure that any cut that I choose, let's say I choose this cut. Oh, okay, sorry, I didn't put the, okay, let's say 1 here. Any cut that I choose, let's say I choose this as my cut. Okay, and it disconnects the graph into two parts, right? Any cut that I choose, from there I want the one with the minimum sum, the sum of the weights, sum of the capacities should be minimum. Okay, that is the weighted min cut. And according to that, which should be the weighted min cut? here. So let's say this is 20. According to the according to the weighted min cut definition.
So the 3 and the edges carrying the weights 3 and 4, 3 and 7.
3 and 7, right? I'll choose this edge. I'll choose this edge. Disconnecting would disconnect the graph. It is a cut, and the sum of the edges, sum of the capacity of C is equal to 7 plus 3, which is 10, and which is minimum if you go across. Yeah, that is the answer. Okay, good. But so interesting thing is what is min flow max. Now I'll come to what is max flow min cut theorem. Max flow min cut theorem says the following. Okay, max flow min cut says the following. Max flow min cut. It says that max flow across network, S to T max flow across network, is equal to the min cut capacity of the network. Okay, so so it means something like this. So let's say this is T, and let's say this is S, and let's say this is 4, 3, and this is 8, and this is 2, 2, 2, 1, and okay. So let's keep it as 3. I just want to give us very simple idea. So 4. Okay, this is a very simple network. What is the max flow? What is the max flow? Okay, let me make it 3. Okay, what is the max flow? Max flow is okay, I'll make this as 4. Okay, max flow is 7. Okay, max flow is 7 here. Why is it 7? Well, let's say I send all 4 units here. I send all 3 units here. Okay, I send all 4 units here. I send all 3 units here. Okay, out of the capacity it's allowed. Then from here, I send 3 units. From here, I send 1 unit. Then from here, I send 3 units. From here, I send 4 units. And I sent 3 units because the input is only 3. And from here, I can combine both and give 4 units. So I can use all the edges and total is 7. It says that the max flow across the network is same as the min cut capacity. Right. And you can see that it works. Okay, but this is a very simple example. It says that the value of the min cut, okay, the value of the min cut is same as the value of the max flow, and max flow is 7, and I find a min cut. What is the example of a min cut here? This is an example of a min cut. Right, this edge and this edge. And what is the capacity? What is the capacity of this cut? It's 4 plus 3. And another example of a min cut is this. It disconnects the graph when I remove it. It's 4 plus 3, which is 7. But I cannot say choose something like this. Let's say I choose this edge and say this is my cut. It is not a cut because it is using more than 2. It is not the minimum cut. Okay, it is a cut, sorry. It is not a minimum cut. And what is the sum? 3 plus 3 plus 1. Oh, okay, sorry. It's still the. Okay, it still works. It's not violating the max flow min cut theorem. It's not violating the max flow min cut theorem. It's not violating it because max flow min cut theorem only says the flow across a network is equal to the cut capacity. Max flow is equal to the min cut capacity. Okay. But it does mean max flow sum of the units. Okay, there's something wrong here. Max flow is always the sum of the. Okay. Sorry. Okay. Sorry. This is also min cut according to a new definition of min cut, of the weighted min cut. Right. Still, it is still a min cut because the sum is 7. It is a cut, and the sum of the capacity, that is, we mean a weighted min cut. It is still a cut. This red set of edges is still a weighted min cut. It is not a min cut in the traditional setting, which is the number of edges is the sum of the capacity is minimum. That is true.
So how did you find min cut here? How did you come to know that these, the red edges are the min cut? Just because the max flow is 4 or what?
So firstly, it disconnects the graph into 2 parts. It is a cut, and the fact that the sum of the capacities across the edges is 7. So it is a min cut.
I could not understand. Why? Because all the flow coming towards the sink and its value is 7. So therefore the max flow is 7. Is this so?
Therefore the max flow is 7. Correct.
Yes. So now, once we know the value of the max flow, then how to, identify the potential edges, which could be the part of the min cut.
So take any, so you identify the max flow, take any set of edges, take the sum of the capacity. Okay.
Sum of the capacities or the sum of the flows?
No, sum of the capacities. Sorry. Sum of the flows.
Sum of the flows.
Take the sum of the flows. If it matches with the max flow, then it is a weighted min cut. It's not a that original min cut where the number of edges are minimized. It's the traditional min cut. You get it right? Sorry, it's not the traditional min cut. It's the weighted min cut where the sum of the capacity, sum of the flows are minimized. Sorry, I was saying capacity. Okay.
Yes, right.
Right.
So then there could be, 3 possibilities of the min cuts here. So there could be 2 blues, 3 reds, or the last 2 blues coming towards the sink, towards the T. So wherever we find that the sum of the capacities, sum of the flow is 7. So can I take the edges like the one like say the red and one blue, and then in the different portions of this graph? So can you assign labels to these vertices? Like say,
Sure. So let's say this is A, B, C, D. Okay, let me write it in black. A, B, C, D.
Yes. So can we take the edges like say I pick one S to A, and then I take B to T.
B to D, yeah.
Yes. So now
Where is B to T?
yes, yes. So
Okay.
now the sum of the flows here is still 4 plus 3 is equal to 7. But then if we remove these two edges, so are we going to get a disconnected graph? I think no.
We are going to get a disconnected graph in a directed. Uh, what is meant by a connected graph? It means that there is a path from A to B to every other node, but that is not the case here. You can see, right? Well,
Uh,
since it's a directed graph.
so yes, but then the idea of the min cut was, I mean, not is not restricted to the directed graphs only, because
No.
in the
Weighted min cut
in
is restricted to directed graphs.
oh, I see. Because in all the previous examples, you took undirected graphs.
I took undirected graphs. I know. I'm sorry. Yeah, with this, for example, it should be directed
Oh, I
because
see.
undirected does not make sense what capacity is. Okay, but yeah.
Oh, I see. So then, if the graph is
But in
directed,
the previous examples I get, they are all undirected. Okay, because we are just talking about simple cuts, not weighted cuts. Yeah, continue.
so this max flow and the min cut problem with this theorem
Hmm.
is relevant only for the directed graphs and not the undirected ones. Is this so?
Yeah, but if you can think about it, you can say that every directed graph can be made an undirected graph, right?
Vice versa, rather the reverse one, because every undirected can be viewed as a directed one.
Yeah,
But
sorry. Every undirected can be viewed as directed one. No? So any
yes,
algorithm that works for directed will also work for undirected graphs.
right, will work for directed, but
But the
but it's like
other way around is not simple. That any algorithm for directed, sorry, every algorithm for undirected may not work in the directed setting. Undirected is always the easier case.
yes. So I mean, after the removal of S to A and B to D, which connectivity gets lost? I mean, where the things are getting disconnected? Because still the connectivity is maintained if we just
Oh
ignore the
yeah.
direct.
Because now um, um, you're trying to solve undirected using sorry, trying to solve a directed using an undirected algorithm.
Mhm, mhm. Okay, okay,
Right.
yes, yes.
But see, it's not just that it's um, the vertices, the edges that you chose, Goel, which is S to A and B to T,
Yes.
is not actually a cut.
This is not cut, yes. This is not cut because the connectivity is maintained somehow among the vertices.
So you need to remove one more edge to disconnect the graph.
But then this 4 plus 3 becomes equals to 7, and that is the value of the max flow. And according to the theorem, then the
Yeah.
max.
But the theorem requires a cut.
Oh, I see. I see. Okay. So the thing is like this, that first, whichever edge we are removing, it should be a cut first.
Yeah.
Then to, include the modified definition of the cut so as to minimize the weights assigned to the edges. Out of those potential cuts,
Hmm.
then we will pick the one wherein we find the max flow.
Right.
Yes. Now I understood. Yeah. Thanks. Yeah. It's
Okay.
clear to me.
Yeah.
Thanks.
Okay. Kishore, you had a question that time, I think.
Yeah. See, even if we cut A to B and B to T, the still graph is getting disconnected because the edge B is getting isolated.
Let me see. A to B and B to
B to T.
T. Yeah, right.
Yeah. B to T. So even it's a continuous edge which we remove. It's still making the graph disconnected, but the min as it is disconnecting, we can say it as min cut, and also the flow is only 6 now, which is getting, and it is mismatching with the max flow.
Yeah. No, see, actually, um, it's not just the fact that, yeah, I've hidden some of the details here in this theorem. It's not just that the edges I can actually remove in random order. Okay. For example, if I remove any two adjacent edges, like you said, I'll always be able to descend the graph into two parts.
So is this something a constraint that we cannot move the continuous edges?
It's not.
For this theorem?
Yeah. Why? Because what we want to do is we want to make the cut such that they move from S to T. I mean, they form two S to T paths. For example, what I mean by that is, if I have,
So it should be two parts where S should be in one part and T should be in one part.
exactly.
Okay.
You want a graph where what the theorem actually intuitively says is that the max flow at any point is the total amount of flow that is getting pushed from S to T. The minimum weighted cut is actually the amount of flow that is getting pushed from S to T.
So in that case, A to B, B to T is not a min cut.
A to T is not a valid min cut according to this particular theory. Okay.
Good.
So let's try to apply this theorem. Okay. And 7:30. Oh, okay. Karger's algorithm is remaining. Okay, let's quickly do this. So the question is, describe how you can use max flow min cut theorem to find a min cut in the following graph. And see that I'm asking for min cut, not weighted min cut. This graph has no flow. This graph has no directed paths. It has no capacities. But still we are getting asked to find the min cut. But still we are asked to do a max flow min cut theorem. Okay.
So
we need so yeah, go ahead.
So I was just throwing an idea that we can convert this undirected into the directed one, number one, and then we can assign
that is something that is very important, because to use max flow min cut you need to use a directed graph. Yeah.
And
Good.
then we assign weight 1 to every edge.
Okay. Yeah.
Okay. We can think of
Yeah. So that is right. So don't let this S and T fool you. Okay. These are not necessarily source and target, by the way. So you can use A, B, C, D, E, F, G. So now here's the interesting thing. Okay, max flow min cut. Now you may say, okay, we are working with weighted min cuts, but we want just min cut. Okay, we don't want weighted min cut. So how do you find a solution to that? Well, if I look at this cut, okay, and I say this is the minimum cut possible. Let's say I claim that this is the minimum cut possible, but I say, okay, add weights on it and still make it the minimum weighted cut. How do I do that? I just assign the capacity to be 1 or weight to be 1, whatever. If I assign the weight to be 1, the capacity of this cut is equal to 1 plus 1 plus 1, which is 3, which is always same as the number of edges. So if I minimize, if I label all the edges as 1 and then minimize, if I label all the edges to be 1 and then minimize the minimize the capacity of the cut, it means I'm minimizing the edges of the cut. Right? If I minimize the capacity of the cut, it means I'm minimizing the edges of the cut, because every edge has a number 1, and if a cut has capacity 3, it means there are 3 edges in the cut. If it has a capacity 2, it means there are 2 edges in the cut, and so on, because capacity is nothing but the sum of edges in the cut. So most of the problem is already solved now, because what I have now is a way to interpret weighted min cuts as min cuts, or weighted cuts as cuts. So, but now what is another problem? I should be having a source and a sink. What is another problem? I should be having the source and the sink. I should be having a directed graph. But remember that every undirected graph is also a directed graph. Okay, how is every undirected graph also a directed graph? Every undirected graph is just a directed graph where there are edges in the both directions, because it means I can traverse both ways. So I do this. And I do this for everything. Okay. And I think everything is almost taken care of. And this guy. I add edges on both sides. Yeah, Kishore.
Yeah. See, given a unweighted graph and then asked us to a min cut, so probably in that case, do we need to consider the number of edges?
Yeah. No. Okay. Yes and no. If you are asked just min cut, you need to consider the number of edges, because the traditional, this is just the standard min cut. It's not asking for a weighted min cut. If I just say cut, it means
provided a graph which is unweighted.
Okay, a graph is given which is unweighted. Is it also undirected?
Maybe it's, see, even if it is undirected or directed, what we have discussed is it can be converted. It defaultly is a directed graph, though it is an undirected graph because it flows through both directions.
See, yeah, undirected can be converted to a directed one, but the other way around is not possible always.
Yeah,
a directed cannot always be converted into an undirected. Okay, yeah.
So let us suppose then unweighted and directed graph.
Unweighted directed. Okay, unweighted directed
graph.
Okay.
So in that case, right, so do we need to consider the number of edges for the min cut?
Okay. Now, if you have an undirected graph which is if you have a directed graph which is weighted, then the idea of a cut may require some specification. Okay, but if it is unweighted, it will mostly be the number of edges only, because there is no other parameter that we can actually quantify with.
Irrespective of directed or undirected, if the weights are given, then we need to think of the some integer value.
Some integer value. But let's say I tell you that, okay, weights are given, but I'm still asking you to find the minimum cut. Then it could mean either things, unless I mention that, okay, minimum weighted cut.
No, see, even if the weights are given, right? If the weights are given, irrespective of number of edges, we'll go with the summation of the capacities, right?
Should mean that only, yeah.
Yeah. Okay. Fine.
Yeah.
That answers.
Okay. Great. So this is what we have now. We converted it to this. Now, notice that the size of a cut. Okay, let's say the original graph, undirected graph, is G1. This one is G2. Okay, this one is G2. Notice that the weighted cut size of any cut C is equal to the normal cut size of cut C, which is nothing but the number of edges. This is what number of edges in C. Okay, because if I take a cut now, okay, if I take a cut now, let's say I take this cut. What is the weighted cut size? It is 1 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1 plus 1 is 8. Sorry. Weighted cut size is equal to 8, and number of edges is also equal to 8. Why? Why is this the case? Because we've labeled all the edges as 1 equal to 1. This is always true. So it means that min cut size, weighted min cut size is equal to the normal cut size, which is the number of edges. In the cut C. This is of graph G2, okay, the converted graph. Right. But what is this in min cut? But what is this? The number of edges is equal to exactly twice the number of edges in min cut of G1 is always equal to that. So what am I going to do? I'm just going to run the max flow algorithm on this, and how do I choose the source and the sink? I'll go across all possible combinations of source and sink. At first I'll choose this as source, this as sink. Then I'll choose say A as source and B as sink, and I'll do it for all possible combinations. How many combinations are there? N square. In this case there are 6 vertices, 6 square many choices are there, and I'll just do that and then go across all of them, and I'll run a max flow algorithm, and because of that I'll get the weight of the min cut. But the weight of a min cut is same as the number of edges in this graph G2, which is same as twice the number of the edges in graph G1. So what is the cut size in the original undirected graph? I just divide by 2. And I'll get the size of the minimum cut, which is the number of edges in the minimum cut of the original undirected graph. Okay. So is that clear?
Can you please repeat the last point, right? So
sure.
In directed graph G2, of course, the number of weight size is equal to number of edges. That's okay.
That is fine.
And second point is the last one.
Twice the number of edges in the minimum cut of G1. It's not just minimum cut, it's in the in terms of twice the number of this guy cut size of any cut C is equal to twice the number of edges in C in the cut C of G. Now, why is this the case? Because every edge is now drawn twice here, as you can see in this new graph G2. One in the original direction, one in one direction, the other in the other direction. Every undirected edge is getting changed to.
Okay. Only this is in case given undirected, we convert it to directed.
Yeah, this is the only reason why we gave both direction, right? Because the rest is, I think, clear. Right, Kishore?
Yeah.
Okay.
That's answer.
Okay. So this is one example of This is another example of how we can use flows to actually find the minimum cut. And by the way, how much time does it take? What is the time complexity? We are going all across all pairs of vertices, which is n square, and then we are running. Okay, so which is number of vertices square, and then we are running a max flow algorithm. Say we are running Ford Fulkerson algorithm. How much time will it take? Well, it will take something like v square. We saw last time, right? And e square is already something like e square is already something like n square v square, so it's like v to the 4, v to the 5, v to the 7. So the running time of this algorithm is around v to the 7, something like v to the 6, v to the 7, something like that. But anyway, it's very bad. Okay, but you can see that it still works. It is still polynomial, right? Okay, so okay, good. So I hope rest also. Are you guys following me? Bhaskar, Sandhya, Ramya.
Yes, sir.
Oh, okay, Ramya. Good. So just please stop me and let me know if you want me to repeat anything. Okay, repeat any point. Okay. Okay, so that is about max flow min cut theorem. Okay, let's. Oh, sad. I won't be. Oh, okay, great, Sandhya. Okay, good. Okay, it's sad I won't be able to cover much. I really wanted to do at least. Okay. 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 Good. Glad to know. Just stop me if you want me to repeat something. Okay, Bhaskar and Ramya, Sandhya. Okay. So okay, now we are quickly going to do Karger's algorithm. Okay, and then if I get time, then we'll do this one. Okay. I'll just take a screenshot and copy this. Copy, delete. Okay, so question is saying use Karger's algorithm to on the following part graph to find the min cut. Now, why did I mention about time complexity? It was something like order. I think you can bring it down to order v to the 6 by choosing only one target vertex, because target vertex shouldn't matter, I think. So the this is by max flow min cut. Okay, this is my max flow min cut. Now what you can do is you can do an improvement on the efficiency of the algorithm, okay, to find min cuts. But this algorithm is a randomized algorithm, which is called Karger's algorithm. Okay, a randomized algorithm which is called Karger's algorithm. What is randomized algorithm? It uses randomness. And what is randomness? It means it has access to what are called random bits, which is akin to tossing coins. Okay, so it tosses coins. We'll talk more about randomization next week. Okay, and it tosses coins on the way. And surprisingly, randomization has a lot of power. Okay, if given access to randomness, you can avoid several worst cases. Okay, because it seems to be that most problems are actually easy on the average case and hard on the worst case. So given access to randomization, random bits, it is possible to avoid several worst cases and actually get a better success probability. So since you have a randomized algorithm, it cannot always be always true. Okay, it cannot always be always successful. If it is always successful, even though it's a randomized algorithm, then it means that your answer is always yes, regardless of what the question is. Okay, so there is always a success probability, and the success probability of Karger's algorithm is very good. It is extremely efficient. It is something like 1 by e to the k. Okay, 1 by e to the k is the success probability. It's 1 minus 1 by. So this is the error probability, you can say. So it makes error only k many times if repeated k times. And each iteration takes something like root v time. So you can already see that if I if I already repeated something like 10 times, then I get a success probability of 1 minus 1 by e to the 10. So it's something like 1000 maybe. 1 minus 1 by 1000, let's say, which is like 99.9% always works. Okay, cases it always works flawlessly. So, okay. Yeah, Goel, you had a question?
No, just I wanted to. I mean, after seeing this complexity, so I thought that can't we randomly assign the values to zeros and ones here, and then we can find the connectivity from S to T by applying the DFS in a reasonable time. So then I can find many traversal paths. So then I apply the DFS multiple times, and probably we can come up with an algorithm which runs faster than this of the order of v raised to the power 6.
Well, you can argue about, say, if you run a DFS, you can definitely go faster. But what about the correctness? You should have a non-zero probability of succeeding.
Okay. Yes.
Right. So I think what you are saying is, okay. So let's say you run a DFS. I think what you are saying is you toss a coin and check whether you want to include that edge in the cut or not.
Yes.
How many min cuts can be there? There can be at most n choose 2 many min cuts. And how many min cuts can be? How many cuts can be there in total? It is a total number of edges that I can choose, which is 2 to the n. So I get something like n square by 2 to the n is your success probability in one run, which is there's an exponential gap.
Yes.
So yeah, you can use the algorithm, no problem, but the success probability is low.
Right.
Yeah, but good question. Okay. Also, try looking into this. Okay, it's a if you see Karger's algorithm, then you will the proof of Karger's algorithm, you'll be able to tell why the number of min cuts is n choose 2 upper bounded by n choose 2 at most. Okay. But yeah, I'll just demonstrate what the algorithm looks like. Okay. So I have this. So the algorithm is as follows. Okay. I don't know. A, B, C. Why did I name it as S and T? A, B, C, B, E, F. Okay. So Karger's algorithm is very simple. Okay. What you do is you randomly choose two vertices. Choose any two vertices. Let's say I choose C and D. Okay. I choose C and D. What I'll do is a process called contraction. It means I take two vertices and fuse them into a single vertex. Imagine I'm contracting them while the edges are still connected. Okay. So contraction means I have two vertices UV. I change it into a single vertex W such that anything for all vertices X, which is incident on U or V, is incident for all X comma W is an edge. Okay, what does that mean? Okay, let me say I contract C and D, suppose, or let me be simpler, B and E. So what it means is I take a single, I consider BE to be a single vertex. Okay, and so first what I'll do is I'll label these edges. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, now what do? I consider it to be a single vertex. Okay, and the rest of these are there, right? A, B, C, F. Now the rest of the edges, okay, I'll have a self loop here, right? I'll have so B is adjacent to E also, but I'll ignore self loops. Okay, but E is adjacent to F. It is also adjacent to B via what? Via edge 9 and via edge 11. Okay, good. And B is also adjacent to A via 7. B is adjacent to C via edge 8. B is adjacent to E is adjacent to D via edge 5. And anything else is there? No, that's all. Okay, so the rest of the edges will remain. Okay, among themselves, whatever they had. Okay, there's a 6 somewhere. Okay, E is also adjacent to A via 6. Okay, yeah, there's something we're leaving out, it seems. Oh no, it's fine. It's fine. Okay. So again, now randomly toss coins and choose what I need to choose what vertex to contract next. Let's say I choose to contract C next. Contract C and B. C and B. Okay. I choose them now. I make the C, B, E. Okay, and it has a self loop through 8, no problem. It has to A, C is okay. Let's first do B. Okay, B is 7, 6, D is 5, and F is 9, 11. Okay, and F to D is 4, A to D is 2. Okay, great. Now we've contacted C. Now C is in contact with D and A through edges D through 3 and A through 1. This is what I get. Right? And now I contract two random ones. I can even choose say D and F. Choose DF. Okay. Choose DF, and I contract these guys. So I get what? DF as a single vertex and 5, 3 CB. Okay, CB one more, no? Okay, no, CBE, that's fine. CBE 53, 911, and A 761. Now what do? I contract A and BF. Contract A and DF. So I get CBE DF and ADF. So I get 5, 3, 9, 11, 7, 6. And this is my cut. I know this is overkill and you could have just disconnected this, okay, and be done with it instead of disconnecting 5, 3, 9, 11. This is such an inefficient cut, right? 7, 6, 1. You may not even get a cut. 6, 1. But you will always get a cut. Sorry. You will always get a cut. That is guaranteed. But look at it. It looks like it's a very bad algorithm, right? But that is firstly because we are using a very small graph. And secondly is we just did one iteration. The more and more iteration we do, the more that it exponentially gets even better and better. I do another one and I do another one. And each time I do it, I find a better and better cut. Finally, I'll stop at a point, will stabilize, and then I'll say that, oh, this is so small, this cut, that I'll just stop, I'm fine with it. And but Karger's algorithm basically is this, okay? And
so where is the randomization here?
Oh, the randomization is this. We chose BE to contract. We chose C and BE to contract. We chose DF. We chose this randomly. Don't be confused between arbitrary and random. Okay, arbitrary means that the order is already fixed.
But then, don't we have some kind of the heuristics? To make this algorithm more efficient.
You could do some kind of heuristic.
Yeah, instead of randomization, we could have made it deterministic completely. Like say, I was thinking of one heuristic, say, wherein we merge those nodes which have got the weighted common neighbor, right? Like say, so last in the second slide, whenever we had
by the way, okay, this is a simple min cut, okay, and by the way, don't interpret these as weights. These are just labels I gave to the edges.
So weight, I mean to say that the number of the numbers, numerals assigned over the age. So can you go to the figure in the next page, next slide?
Okay.
So yeah, this one at this point. So at this point we merged, say A with DF. So we could have merged, say, CVF with the DF kind of the thing, because here we have 5, 3, 9, 11. Say we have 4 numerals over the age, and whereas for the ADF we have got 2. So I was under the impression that somehow we can take this common neighbor kind of the thing into consideration. So
right.
Thing,
you would want to, right. So if you would want to contract those edges, one heuristic can be you would want to contract those edges which have lots of labels. For example, if you contract this, it's better for you than say contracting this guy, because you're only absorbing 2. If you absorb this, then it means all these edges you are collecting them, because finally, what is the cut that you achieve? Finally, the cut that you achieve is whatever remains, the labels that remains on the either side of the contracted vertices. So it's better to absorb long labels, right?
Yes, and there could be other heuristics as well. But
you could have other heuristics. For example, degree. You would want to contract high degree vertices, or is it the opposite? You would want to contract low degree No. You would probably want to contract higher degree. That's what I think.
So I mean, how to? So then, how to show that that the success probability is pretty high?
Okay. Let's see. So what is the heuristic you want to choose?
So I mean, this time
Let's
we
say the
can
label length.
label. Yeah, fine.
Okay. Um, so it's not introducing randomization. So heuristics is always a bit um, the side of heuristic algorithms. It's there's no probabilities associated with it. So it's slightly a vague term about analyzing heuristics. But let's see. Let's try. Let's say you want to say that if I choose the longest label, I will always get a better algorithm, right? Intuitively, it makes sense. Intuitively, it makes sense because if I choose a longer label, okay, if I choose a longer label, then I am going to absorb that, and probably I'll have shorter labels here, and that is going to work for me because instead of if I had instead of choosing ADF, I had chosen these two guys. Then wait, just one moment. It looks like I'm out of charge. Okay, I need to charge. If I choose these two guys, then the graph that I get is CBEDF and 2761 and A. This single choice of choosing a longer label is causing me to have a smaller cut. Right. This is an example. This is not a proof. What you would want is a proof. I can give a proof to you that saying that I can give a proof to you saying that this is at least as efficient as the previous one, but saying that it is always more efficient, that is not clear, and it requires a lot of analysis that I can already tell. But one small point that you can do is if you choose this following heuristic, okay, that you look at the lengths of the labels, okay, for example here, and I look at a label and choose its length, see its length, it's of length 4, and look at this label, it's of length 3, and this length is 1. I would not want to contract when, if after contracting, the remaining edges, their sum is greater than what I've already contracted. This is the trick that is getting played here. Because see, if I contract this guy, I am getting a 4 length label here, which is still fine. But the fact that I contracted, the fact that I contracted 2 here, the remaining sum is what? 1, 2, 3, 4, 5, 6, 7. 7, which is much larger. I would not want to contract that because you can see that, and you can even prove it. You can even prove it. The proof should not be very difficult, and but on analyzing it would take some work, I think. But I'll look into it. If I find a neat way to analyze the heuristic that you are talking about, then I'll discuss it next class. Okay. And okay, so it's way past 8. Okay, it's 10 minutes past 8. I'll just tell you this is a simple question on bipartite graphs. Please try it. I could not discuss the matching questions. I'm really sad because of that. I could not do matching, so maybe next time I can do it. Please try these questions. Okay, find maximum matchings here. Okay, I'll just let you know, you'll use what is called the augmenting paths algorithm to solve this. And to solve this, you need to look at Edmond's Blossom algorithm. Okay, please try this. And this is another matching question that is quite simple. Okay, so that's it. Anyone has any other questions, please stay back. I'll be happy to address it. Otherwise, we can stop the class. Okay, and
Yeah,
yeah, it's past the time. So if anyone wants to leave, also then please leave. Okay, yeah.
yeah, this right, Karger's. So we have taken for this example, we have taken the undirected graph. So is the same what we have discussed applies on the directed graph as well?
That is a good question. If you have weighted directed graph, you mean?
Yeah.
Yeah, just one moment. Okay. Um, Personally, I do not think so. I cannot tell you for sure. Okay, but one thing I can tell you is, okay, just one moment. I stopped sharing my screen. But one thing I can tell you is, um, okay, one moment. See, every undirected graph is a directed graph, but every directed graph is not an undirected graph. So the same analysis techniques will definitely not work here. For Karger's algorithm, if you use the same techniques, what he has done is he has computed the probabilities by looking at the um, notes of by noting the uh, number of edges here. What is the number of edges you? It's a very combinatorial approach. Okay. Once you add the weights, the same analysis will not work. You try computing the probability. You look at the proof of not Edmund Blossom, Karger's algorithm.
Karger's. Yeah.
Right. And the same proof will not work. You cannot prove success probability in the same way. That thing is for
Okay,
sure. So now you say
Karger's is only meant for undirected graph, undirected and unweighted graph.
Yes, unless what you can do is unless you can, it may be, what I mean is that it may be true that if you choose randomly edges, maybe it will work for directed weighted graphs also, but the same argument will not work. That is what I'm saying.
Okay.
So the thing is, the most important thing about algorithms is, see, the time complexity is easy to prove. It is proving correctness that is slightly difficult, which in the case of Karger's algorithm is its high success probability. Let's say you do random weight assignments also. This is particularly true about randomized algorithms. If you look at randomized algorithms, the algorithms are very simple usually. A lot of algorithms are just, you randomly toss a few coins and choose that as your parameter and then proceed with the algorithm. But
Yeah.
But the analysis is the important thing. How well can you analyze? Because if you are given random weights, if you are given some weighted and directed graph, I can always do a trivial analysis and tell you that, okay, your algorithm is really bad. But I need to come up with a better and better analysis techniques. Because if you look at Karger's algorithm, he did nothing really ingenious, right? He was just randomly picking and contracting. And contracting is a very common thing in graph theory. It's not a very new thing. It's a very simple algorithm that he has. But the fact that he came up with a great analysis of his algorithm is what the nice thing about it. And it's particularly true about randomized algorithms. You see research happening in sublinear algorithms, randomized algorithms, where there are randomizations happening. There are already standard algorithms, but people publish research papers that show that, I've come up with another analysis technique that shows that this standard algorithm is actually working better than we expected.
Yeah.
Okay.
Yeah.
Yeah. Okay. Any other question? And please try these questions. Okay. I am going to upload it in the Google Sheet. Last time I was a bit slower in uploading because turns out I had an issue with the recording. So this time I hope it recorded well. I'm going to upload it also. And please, if you cannot make it to the class, then at least please watch the video. And uh, but at the same time, please try to attend the problem solving sessions also. I encourage that. There's a good interaction that happens. Okay. Okay, so the next week's content is randomized algorithms. Okay, and we'll be getting into that, which is a very exciting area, and it'll be happening again on Tuesday 6 p.m. Okay, so no questions, I think, or are there any more questions?
Oh, yeah. Thank you very much.
Okay, thank you, Paul.
Bye. Interesting session. Bye.
Okay, thank you. Yeah. Okay, thank you, Ramya. Okay, thank you, Kishore. Okay, thank you. See you next week. Okay, Bhaskar. Thank you. Good night. See you next week. Okay, Bhaskar. Thank you. Okay, thank you, Santha. Good night. I think everyone is very hungry right now. Okay, bye.